You see it everywhere, don't you? Hung in every science classroom, adorning textbooks, even printed on coffee mugs for the truly dedicated. The periodic table of elements. A pillar of modern science, a testament to human ingenuity. Seemingly as fixed and unyielding as the laws of physics themselves. We glance at it, admire its elegant order, perhaps recall a few element names, and then move on, assuming its creation was a straightforward, almost inevitable march of progress. A logical conclusion born from brilliant minds, presented neatly, perfectly, without a wrinkle. But what if I told you that the story you've been fed, the one etched into the annals of conventional science history, is merely a polished facade? What if the truth behind this iconic chart is far messier, infinitely more human, and profoundly more captivating than any textbook dared to suggest? Because, believe me, the periodic table didn't just appear. It wasn't meticulously crafted in a sterile lab by a lone genius. Nor was it the culmination of a perfectly orchestrated scientific ballet. Oh no, its genesis was a tumultuous, often chaotic, and utterly gripping saga, teeming with eccentric personalities, bitter rivalries, moments of sheer desperation, and even strokes of blind, inexplicable luck. Imagine, if you will, the world of chemistry in the mid-19th century. It was not the sleek, organized discipline we know today. Far from it. Picture dimly lit laboratories, often in the damp basements of universities or in the cramped, smoke-filled attics of ambitious, self-taught experimenters. The air thick with the acrid scent of sulfur, the metallic temps of mercury, the sweet, cloying aroma of newly isolated organic compounds, glassware of all shapes and sizes, from delicate retort flasks to robust distillation apparatus, precariously stacked, glinting in the flickering gaslight, handwritten notes, smudged with reagents and charcoal dust, piled high on wooden desks, scarred by acid spills and burn marks, alongside crude, hand-drawn diagrams that struggled to capture the elusive nature of atomic structures. It was a frontier, a wild west of discovery, where new elements were being unearthed at an astonishing, almost overwhelming, pace. Every year, it seemed, another shiny metal, another volatile gas, another curious solid was pulled from the earth or painstakingly synthesized in a bubbling flask, adding to the growing roster of fundamental substances. But here was the profound, gnawing problem that kept countless brilliant minds awake at night. There was no guiding principle, no grand organizational scheme to make sense of this rapidly expanding universe of matter. Scientists, scattered across continents, each working in their isolated intellectual silos, were grappling with a bewildering array of facts. They knew hydrogen was light, gold was heavy, oxygen supported combustion, and chlorine was a deadly gas. They could describe properties, conduct reactions with increasing precision, and isolate new substances with remarkable skill for their time. Yet the deeper understanding, the predictive power, the ability to see the underlying connections between these disparate building blocks of the universe, remained stubbornly elusive. It was like having all the letters of the alphabet, but no grammar, no syntax, no dictionary to arrange them into meaningful words, let alone eloquent sentences that could convey the universe's secrets. The sheer volume of isolated elements, each with its own unique set of characteristics, felt less like a comprehensive library and more like an overflowing unindexed archive. The frustration was palpable, a collective groan echoing through the hallowed halls of academia and the solitary confines of private studies. Imagine spending years, decades even, meticulously documenting the properties of a dozen elements, carefully measuring their atomic weights, only to find your hard-won knowledge seemed to exist in a vacuum, disconnected from the equally diligent work of a colleague across the channel or even in the next city. Every new discovery, while exhilarating, also added another piece to an already overwhelming, jumbled puzzle, making the grand unification seem ever more distant. How could one compare, predict, or even truly comprehend the fundamental nature of matter when its very constituents seemed to defy any logical arrangement, any discernible pattern? The scientific community, though burgeoning with brilliant minds, was drowning in data, longing for a framework, a Rosetta Stone that could translate the chaos into cosmos, transforming a mere list of elements into a predictive map of reality. They yearned for order, for patterns, for the underlying rhythm that surely must govern the elements. But the path to that rhythm was anything but smooth. It was paved with countless missteps, brilliant failures, fierce disagreements, and the quiet, often unacknowledged contributions of individuals whose names rarely grace the pages of history. We're not just talking about the celebrated giants. We're talking about the forgotten pioneers, the tireless researchers who laid crucial groundwork, the rivals who inadvertently pushed each other to new heights, and even the moments of sheer serendipity that nudged progress forward. My journey into this untold story has revealed a tapestry far richer, far more dramatic than I ever imagined. It's a narrative that reveals the raw human spirit behind scientific endeavor, the burning ambition to unlock nature's secrets, the bitter jealousy over perceived slights, the sudden, blinding flashes of insight that arrive unbidden, and the sheer, unyielding grit required to wrestle understanding from the vast, terrifying unknown. So, Prepare yourself, because we're about to peel back the layers of myth and legend, to venture into the smoky, chaotic laboratories of the past, and to meet the extraordinary characters both celebrated and unsung whose struggles, rivalries, and strokes of luck truly forged this scientific masterpiece. Are you ready to discover the gripping, human story that conventional textbooks never dared to tell? Our journey begins not with the definitive table, but with the very first tentative steps into the elemental unknown and the curious minds who dared to ask, what if? Our journey into the elemental unknown begins not with a grand revelation, but with quiet, persistent questions echoing through the scientific communities of the early 19th century. Imagine the scene: European universities, their stone walls steeped in centuries of tradition, yet their laboratories buzzing with a new kind of restless energy. In Jena, Germany, a man named Johann Wolfgang Deberina, a professor of chemistry and pharmacy, was meticulously weighing, reacting, and observing. His lab was a fascinating blend of the old and the new: heavy wooden benches scarred by chemical burns, shelves lined with rows of glass bottles, some stoppered with ground glass stoppers, others with rough corks, all filled with powders and liquids of various hues. The air, thick with the smell of reagents and the faint, sweet scent of newly synthesized compounds, was illuminated by the soft glow of gaslight, casting long shadows as he painstakingly recorded every measurement in his ledger. Deberina wasn't looking for a grand theory of everything. He was a practical man, a keen observer. What he noticed, however, was subtly profound. As he worked with elements, specifically those that shared similar chemical properties, say, lithium, sodium, and potassium, all soft, reactive metals, he started to see a curious numerical relationship. He found that if he arranged these three elements by their atomic weights, the atomic weight of the middle element was almost exactly the average of the other two. He called these groups triads. Chlorine, bromine, and iodine formed another triad. Calcium, strontium, and barium, yet another. Ed was a whisper of order, a tantalizing hint that beneath the bewildering diversity of elements, there lay a mathematical harmony. His findings were met with a mixture of intrigue and polite dismissal. Interesting, colleagues would nod. A curious coincidence. But it was just that, a coincidence seemingly limited to a handful of elements. It didn't offer a universal framework, couldn't predict new elements, nor could it explain why these relationships existed. It was a small, perfectly cut gemstone, but it wasn't the key to unlocking the entire geological vault. Yet, it was the very first crack in the wall of chaos, the first public acknowledgement that perhaps, just perhaps, elements weren't entirely random. It showed that atomic weight, a property then only just beginning to be precisely measured, might hold the secret. Decades later, in the bustling, intellectually vibrant Paris of the 1860s, another mind, far removed from the typical chemical establishment, took a bolder, more imaginative leap. Alexandre Emile Beguier de Champcatois was a geologist, a cartographer by trade, not a chemist. Picture him in his study, perhaps surrounded by maps and geological specimens, not bubbling beakers. His was a mind that sought patterns in landscapes, in the layers of the earth. He looked at the list of known elements, now numbering over 60, and saw not a flat list, but a potential three-dimensional structure. His idea was revolutionary in its simplicity, yet tragically complex in its communication. He proposed arranging the elements by increasing atomic weight along a spiral drawn on the surface of a cylinder, what he called a telluric helix. As he meticulously plotted each element, he observed something remarkable. Elements with similar properties would align vertically on the cylinder, directly above or below each other. It was a visual, almost tactile representation of periodicity, a beautiful spiral staircase where each step up brought you back to a similar chemical neighborhood. His discovery, published in a dry geological journal, was a stroke of genius. But here's where the human element, the untold story, truly bites. De Champcatois, the geologist, failed to include his crucial diagram in the published paper. He wrote about it, described it, but the visual aid, the very essence of his breakthrough, was either lost in translation, deemed too unconventional by the editors, or simply forgotten. The chemists of the time, reading a geological paper without its critical illustration, simply couldn't grasp its profound significance. His work, so close to the truth, vanished into obscurity, a brilliant idea lost in translation, a testament to how crucial presentation can be in the unforgiving world of scientific acceptance. Then, just 2 years later, across the English Channel, an industrial chemist with a passion for music would rekindle the flame of periodicity, only to have it brutally extinguished by ridicule. John Newlands, working in a sugar refinery in Canning Town, East London, was a methodical, self-taught man whose days were spent analyzing sugar and experimenting with fermentation, but whose nights were dedicated to the grander mysteries of matter. His laboratory would have been a stark contrast to the academic holes, perhaps a corner of the refinery, filled with the sweet, heavy scent of molasses, the clanking of machinery, and the distant hum of the industrial city. Newlands, inspired by the orderly progression of musical scales, noticed that if he listed the elements in order of increasing atomic weight, every eighth element seemed to exhibit properties similar to the first, just like the notes in a musical octave. He called it the law of octaves. It was a bold, elegant proposition, and he presented it to the Chemical Society in London in 1866. The reaction was swift, brutal, and humiliating. The august members of the society, steeped in traditional empiricism, found his analogy to music unscientific, even whimsical. One particularly scathing remark, often recounted with a sneer, was from Professor George Foster, who acidly asked if Newlands had ever thought of arranging the elements according to the initial letters of their names. The room erupted in laughter. Newlands's law was dismissed as a mere curiosity, too simple, too mystical, and riddled with imperfections, especially for heavier elements, where the octave pattern broke down. He had even been forced to place two elements in the same box in some instances, and some similar elements ended up in different octaves. The scientific establishment, resistant to anything that felt less than rigorously proven, saw only the flaws, missing the profound truth hidden within his imperfect arrangement. Newlands, a man of quiet conviction, persevered despite the scorn, continuing to publish his ideas even though they were largely ignored. It would take years for his genius to be belatedly recognized. What strikes me about Dmitri and Newlands is not their ultimate failure to create the definitive table, but their shared burning desire for order, each, in their own unique way, with their own particular blind spots and strokes of bad luck, chipped away at the colossal problem of elemental chaos. They were all driven by the same fundamental curiosity, the same knowing feeling that beneath the apparent randomness, there had to be a pattern. They were pioneers, charting unknown territory with imperfect maps and rudimentary tools. Often ridiculed, often overlooked, their work, though incomplete, was essential. It proved that atomic weight was indeed the key, and it demonstrated, perhaps more importantly, that periodicity, the recurring patterns of properties, was a real phenomenon, not just a figment of an overly imaginative mind. They had laid the groundwork, illuminated the path, but no one had yet built the bridge. The world was still waiting for someone who could not only see the pattern but understand its underlying logic, someone who could predict the unknown, and, most importantly, someone who could convince a skeptical scientific community who would be the one to finally piece together this cosmic puzzle. And what extraordinary sacrifices, what bitter rivalries, and what moments of sheer serendipity would lead them to the grand. The world was indeed waiting. The whispers of order from Dmitri, the lost genius of Dmitri, and the ridiculed insights of Newlands had all pointed in a similar direction. Atomic weight held the key, and patterns, like echoes in a grand hall, recurred, but no one had yet provided the definitive, predictive map. As I delved deeper into this era, I discovered that the solution didn't emerge from a single blinding flash, but rather from a convergence of brilliant minds, each wrestling with the same colossal problem, often simultaneously, often unaware of the other's progress, yet inevitably destined to clash in the annals of scientific history across Europe. In the mid-1860s, two men, seemingly worlds apart in temperament and circumstance, were independently closing in. In Germany, Julius Lothar Meyer, a meticulous, quietly brilliant academic, was painstakingly collecting data. I picture Meyer in his well-ordered laboratory at the University of Karlsruhe, perhaps a stark contrast to the chaotic Wild West labs I described earlier. His glassware would be spotless, his instruments calibrated with obsessive precision. He wasn't one for grand pronouncements or dramatic flourishes. His genius lay in his methodical approach, his unwavering dedication to empirical data. He was fascinated by the physical properties of elements, particularly their atomic volumes, how much space an atom of each element occupied relative to its mass. As he plotted these values against atomic weight, he began to see a magnificent undulating curve emerge, a clear, beautiful rhythm that repeated itself. Peaks corresponded to highly reactive metals like lithium and sodium, while troughs represented less reactive elements. It was a visual testament to periodicity, a graphical representation of the same patterns Newlands had glimpsed through his musical analogy, but grounded in hard, undeniable data. Meyer was building a table, yes, but it was his elegant curves that truly spoke volumes, revealing the ebb and flow of elemental properties. He published an early version of his table in 1864, laying out 28 elements, but crucially, he didn't emphasize its predictive power. Nor did he publish his more comprehensive table and his iconic atomic volume curve until 1870, a critical delay that would impact his historical recognition. He was a scientist of profound depth, but perhaps lacked the audacious spirit of his contemporary. Meanwhile, over in St. Petersburg, Russia, a very different kind of mind was at work. Dmitri Ivanovich Mendeleev was a man of fiery passion, restless intellect, and an almost evangelical zeal for chemistry. He wasn't just a researcher, he was a dedicated teacher. Frustrated by the lack of a suitable textbook for his students, he needed a way to organize the overwhelming amount of chemical knowledge into something comprehensible, something that could be taught. I imagine him in his study, not a pristine lab, but a cluttered, smoke-filled room, overflowing with books, notes, and the lingering scent of his beloved tobacco. Unlike Maya, whose focus was more on physical properties, Mendeleev was obsessed with chemical behavior, how elements reacted, what compounds they formed, their valencies. He was driven by a deep, almost intuitive belief in an underlying order. His method was legendary. He wasn't simply listing elements, he was playing a cosmic game of solitaire. He wrote the name, atomic weight, and properties of each known element on individual cards, imagine dozens. Then scores of these handwritten rectangles, scattered across his desk, perhaps even his dining table. He moved them around, rearranged them, trying every conceivable permutation, searching for the perfect fit. He'd try grouping them by atomic weight, then by their bonding capacity, then by their reactions with oxygen or hydrogen. The air in his study would have been thick with his frustration, punctuated by moments of sudden insight. He was looking for the grammar of the elements, the syntax that would allow them to form coherent sentences, to tell their story. The aha moment, often romanticized as a dream, was likely the culmination of years of this intense intellectual struggle. Whether it was truly a dream or a waking epiphany after countless hours of shuffling those cards, the result was the same, a sudden profound vision of order. He saw that if he arranged the elements by increasing atomic weight, and then broke the rows, similar properties would indeed recur at regular intervals. But here's where Mendeleev's genius truly exploded beyond mere observation. He wasn't afraid to leave gaps. Where an element didn't fit the pattern, he didn't force it. He left a blank space. And not only that, he predicted the existence of these missing elements, going so far as to describe their specific properties, their atomic weights, densities, even how they would react. He called them ecoboron, ecoluminum, This was an act of breathtaking scientific bravery, to not just organize what was known, but to foretell the unknown based on the logic of his table. That was the leap that distinguished him. Mendeleev published his first complete periodic table in March 1869, beating Maya to the punch by a crucial year. His paper, The Correlation of the Properties and Atomic Weights of the Elements, was concise, confident, and packed with his bold predictions. The scientific community, still reeling from Eulance's musical misstep, was initially wary. Some saw it as another quirky attempt at order, others as a grand, unproven hypothesis, predictions. They might have scoffed in their polite academic circles. Such audacity. They remembered Eulance's flaws, his forced fits, but Mendelev's table was different. It had a logical consistency, an internal harmony that was hard to ignore. The stage was set. Two brilliant minds, working independently, had arrived at strikingly similar conclusions. Maya, the precise empiricist, had found the rhythm in physical properties. Mendeleev, the visionary teacher, had found it in chemical behavior and, more importantly, had dared to use it to gaze into the future. The question now was not if the pattern existed, but whose vision would prevail. And more critically, would the universe validate their audacious predictions? Would those blank spaces on Mendeleev's table remain empty, or would they soon be filled, proving his genius beyond a shadow of a doubt? The answer would shape the very future of chemistry.